Hello and welcome to our lesson on inverses of rational functions. Before we get started with the inverses of rational functions, I just want to do a little recap of some of the things we talked about in regards to inverses in our first module on functions. So if you recall, we focused on linear functions when we were finding inverses, but what was an inverse function? So an inverse function, first of all, only one-to-one functions are going to have inverses. Okay, but if we have a one-to-one function, which we do here, every x has one y, every y has one x, the graph of this linear function would pass both the vertical and horizontal line tests. But if this linear function, if we were to go about finding the inverse for this linear function, it would contain the opposite operations. And to make sure that we were undoing those operations in the correct order, we said we can find this inverse by, instead of having this function solved for y, we could rearrange it, we could solve it for x. So if we, let's say, subtracted 1 from both sides, then y minus 1 would be equal to 3x, and then let's say we divided both sides by 3, then we would have x all by itself equal to y minus 1 all divided by 3. So this is technically our inverse function, but from this point, we took a couple of extra steps just to make it look like a function again. So we were to switch the x and y, and then to call this the inverse, we'd use the little -1 there as a notation. But technically, solved for x, it's the same thing. This is the inverse function, okay? It's got the opposite operations, right? Plus 1 minus 1 times 3 divide 3, undone, excuse me, in the correct order. We just make it look more proper by switching the x and the y and using the inverse notation. Okay, so a couple things to review. All one-to-one functions have inverse or opposite functions. And if you recall, the inputs and the outputs for the function its inverse were switched. So remember, we could do a quick check here. If I plugged, let's say, let's change colors. Let's say I plugged a 0 in here for x. If I put 0 in, 3 times 0 is 0 plus 1 would be 1. So if plugging 0 into the original function produced 1 as an output, then the reverse should happen here. If I input a 1, I should be able to get a 0. So if I put a 1 in here, 1 minus 1 is 0 divided by 3 is in fact 0. So the x, or input here, becomes the output here. So the x switches places, and the input here, the output here becomes the input here, so that switches places, okay? So the inputs and outputs for functions inverse are switched, which makes sense, right? We rearrange the whole thing, and then we switch the x and the y. And then the notation for f of x would be f inverse of x, or if we had g of x, then we'd be looking at g inverse of x, or if we just had y, then we would be looking at y inverse. So we use the little -1 as notation for inverse, okay? Now we're going to be looking at finding the inverses of rational functions, so fractions of polynomials. The process is a little more complicated than with solving the linear types, but it is in fact the same process. But before we get into it, I just want to show you, before we do all of the steps, if I took this rational function and solved it for x, just like here, I started with this linear function and I solved it for x. If I got x all by itself, before we take the step of switching the x and the y and using the inverse notation, if I just solved it for x, technically these two functions are exactly the same. They're just in different forms, right? So here, I have a rational function and I have solved it for x. So these are two equivalent functions here. One's just in terms of x, one's just in terms of y. One's solved for x, one's solved for y. But it is the same function, just rearranged. Now what is the point here, or what I want to show you, is why one form is more helpful than the other. So the original function, when it's solved for y, hopefully we can see, just by looking at this rational function, we can see the restriction. Sorry, I'm all choked up here. We can see the restriction for x. I can tell just by looking at that that graph is going to have a vertical asymptote at 1, because the 1 as an x value going in there would make a 0 on the bottom of the fraction, and that's no good. Now if I rearranged it and solved it for x instead, what we're going to notice here is a restriction for y. We would say, in this one, y could not equal 3 because it would make that denominator 0, which means we would have a horizontal asymptote at y equals 3. Now, earlier in the unit, I told you, well, if these degrees were equal, right, we could just divide our leading coefficients to see the horizontal asymptote at 3. Well, what happens is when we do the rearranging, the solving for x, that restriction shows itself in the bottom of the fraction here. So the inverse is helpful because it shows us, instead of the restriction for x, the restriction for y. Okay? So when the function is solved for x, oh my gosh, I'm so sorry. When the function is solved for x, we can see the restriction for y. The restriction for y. So again, here we could see that x can't be 1 because it would make a 0 in the bottom of the fraction, so that would create a vertical asymptote. And then here we can see that y can't be 3 because it would make a 0 in the bottom of that fraction. Okay, so we can see the vertical asymptotes when it's solved for y, and we can see the horizontal asymptotes when it's solved for x. So I showed you a different way to find the horizontal asymptotes so that we don't have to do all that work, but this is part of the reason why it's helpful to be able to have and look at the inverse function. Okay, so how do we go about getting from the y equals to the x equals version? So first of all, if we have function notation, if we have an f of x in there or a g of x, let's replace it with a y. It just makes the solving process look a little cleaner. Okay, you don't have to do that step, but I prefer rearranging with a y there instead of an f of x, but either way. Then we need to go about solving for x. How do I get x by itself? So let's look at this first example before I give you some of the steps. If I wanted to solve this equation for x, what do I do? It's not so clear as like this guy, right? I know to get x by itself, I can get rid of plus 1 with minus 1, get rid of times 3 with divide 3. But here, I can't get rid of minus 4 with plus 4 because it's on the bottom of the fraction. This fraction thing is holding up my process. So what I'm going to do is I'm going to make this side a fraction too. Like, okay, so if one fraction makes a problem, let me make another fraction because two fractions makes less problems? No, actually, it does. When you're looking at this, you should be recognizing one fraction equal to one fraction as a proportion, and we know how to solve proportions. How do we solve a proportion? We cross multiply. If I cross multiply here, 1 times 1 is going to be 1. And if I cross multiply here, then y is going to have to distribute to x minus 4. So 1 is going to equal xy, or yx, doesn't matter, and then negative 4y. And now I'm trying to, remember, get this x by itself. So now I can add the 4y to both sides. That's going to cancel that guy out. So now I have 1 plus this 4y equal to, I still have the xy on this side. And again, I'm trying to get x by itself. If it's being multiplied by y, then my next step would be to divide both sides by y. So that cancels that. And then I have x all by itself equal to 1 plus 4y over y. Okay? So just to recap, this form shows me a vertical asymptote at x equals 4 because restriction of x is 4. And then in this form, I can see there's going to be a horizontal asymptote at y equals 0 because there's a restriction of 0. Okay? Now that's just a side note. But I want to finish calling this the inverse function. So once it's solved for x, we have to so I don't know what is going on. I'm so sorry. We have to switch x and y, but let me get this right in the right color. This was 1 plus 4y over y equal to x all by itself. Okay, so we're going to switch x and y. Go here for this. So it's y equals 1 plus 4x over x, and then we want to call this the inverse by just putting the little negative 1 here. So 1 plus 4x over x. That is technically our inverse function. Okay. Now remember what we could do to try to check. technically the verification, the algebraic verification, involved the compositions. I don't know if you remember that, but we're going to see that again at the end. But if I wanted to just do a quick check, I could pick something to plug in, like a 5. Let's say I plugged a 5 in here. 5 minus 4 is 1, and 1 divided by 1 would be 1. If plugging 5 in here produces a 1, then plugging a 1 in here should produce a 5. So if I put a 1 here and here, 4 times 1 is 4 plus 1 is 5 divided by 1 does in fact make a 5. So it's just a quick way for me to verify that this is the inverse. Okay, so there it is. Let's go back and fill some steps in. To solve for x, we're going to make a proportion. So one side's a fraction, let's make the other side a fraction by putting a 1 underneath the y. That way we can cross multiply to solve. Okay, and let's see, get all the terms. This is a step that's going to come in a few minutes. So we were going to make a proportion we could cross multiply to solve, and then once we've solved, we can switch x and y, and then write with our correct inverse notation. Okay, I'm going to come back to those other bullets in a little bit here. Let me change colors. Okay, so let's try to solve this for x. I'm going to make a fraction and cross multiply. 1 times x is x. And then here I'm going to distribute y to the x plus 5. So x equals xy, or again yx, doesn't matter, plus 5y. And now this one is a little different than the last one. In this last one, at this step here, if I was trying to solve for x and only one term had an x, I could just add, subtract, divide to get that one term with the x all by itself. But this one is a little different because I have two terms with x's, right? I've got a term here with an x and I get a term here with an x. So I can't just get one x by itself when there are two terms with x's. So the question is, what do I do? Well, I'm not sure if this thought is occurring to you, but I'm going to start by getting both of the terms that have an x on one side. So I'm going to make this x minus xy equal to 5y. So this will be the process. Everything that has an x you're going to want to have on one side, and everything that doesn't have an x you're going to want to put on the other side. Okay? Now why? Why do I want this to be the case? Well, because if these two terms have an x in common, then what I can do is factor that x out. If I factor out the x they have in common, what's going to be left? Well, x divided by x is going to put a 1 here, and then negative xy divided by x is going to leave me a negative y here. Okay? Change colors again, see it again. I'm going to factor out the x that these two terms have in common. So if I take away the GCF here of x, I'm going to have a 1 minus y left, and then I still have the 5y on this side. Now, why was it helpful to factor out the x? Well, now I just have that 1x there, and I can get that 1x all by itself. If it's being multiplied by 1 minus y, to get rid of that multiplication, I can divide. So I'm going to divide both sides by 1 minus y. That cancels that out, and then I'm done. My x is all by itself equal to 5y over 1 minus y. So remember, this is the form that shows me my vertical asymptote, x can't be negative 5. This is the form that shows me my horizontal asymptote, y can't be positive 1. Alright, but that's a little side note. Now let's finish getting our inverse here. We're putting this in the proper form, so we're going to switch x and y. So I'm going to make this y equals, why did I change to blue? Guys, I am just, yeah. We're going to make this a little more fluid. Y equals 5x over 1 minus x, and then I want to call it the inverse. So y inverse is 5x over 1 minus x. And that is my inverse function. Okay? So let me go back up here. Let's fill in these last couple of bullet points. We are going to make a fraction across multiply. If we have multiple terms that contain x's, let's get everything with an x on one side and all the terms without an x on the other side. That way we can factor out the x in common and get ourselves that 1x. Okay? Then we can divide to get x by itself, and switch x and y, write the inverse notation, call it a day. Okay? So let's try that again. Let's see. So this one has the function notation. I'm just going to replace it. I'm going to replace this with a y, just makes the solving a little easier, okay? And I'm going to go ahead and make this a fraction by putting a 1 under it. So let me cross multiply. X plus 1 times 1 is still going to give me an x plus 1 here. On the other side, I have to make sure I distribute the y to the x minus 3. So x plus 1 is going to equal xy minus 3y. And now we have a similar situation that we had in the last one. Two terms have x's. And this time we have two terms that don't. So everything with an x on one side, everything without an x on the other. And it doesn't matter which way you move the terms, but I typically take the x's to the left, but it's whatever. So I'm going to do two things at once here. I'm going to use green, subtract xy to this side. Right, that cancels it from that side, gets the two terms with x's on the left, and I'm also going to subtract the 1 to both sides to cancel this guy out. So now I have two terms with x's on one side, the two terms without on the other. So what I have is an x minus an xy here, and a negative 3y minus a 1 on the other side. Okay, now these two terms have an x in common, so I'm going to factor that x out, which will leave me 1 minus y. And now I can get that 1x by itself with division. X is being multiplied by 1 minus y, so I'm going to divide both sides by 1 minus y. So that cancels, and that leaves me, let's see, x all by itself equal to negative 3y minus 1 over 1 minus y. Now I want to switch the x and the y. So y equals negative 3x minus 1 over 1 minus x. And then I want to write this with the correct inverse notation. And I'm not just going to put the little negative 1 on the y, because this time I started with f of x. So I want to call this f inverse of x equals negative 3x minus 1 over 1 minus x. And if you could do this in less steps, that's fine. I just don't want to lose anybody, so I'm trying to show all my work here. Okay, so there it is. Now, if you're feeling good about this, you want to give the next one a try, this would be a good place for you to pause the video and try it out. Otherwise, let us do this together. Again, I'm going to make this a y over 1, and I'm going to cross multiply. So 3x plus 2 times 1, still going to be 3x plus 2. It's going to be equal to here. If you can distribute, like, just looking at this and not having to write that extra step, that's totally fine. But y needs to distribute to 5x plus 4. So we've got 3x plus 2 equal to 5xy, and then plus 4y. And now I've got two terms with x's, two terms without, so let's do some rearranging here. Let me subtract the 5xy over, and then let me subtract the 2 over. And so now I should be in good shape. On this side, I have a 3x and a minus 5xy. On the other side, I have a 4y minus 2. Now I can factor out the x in common here. If I factor out the x, I'm going to have left a 3 minus 5y. And now I can get that 1x by itself. So I'm going to divide both sides by 3 minus 5y. And there it is. X is all by itself, equal to 4y minus 2 and 3 minus 5y. Okay? So now let's just finish this up. We're going to switch x and y. So y, why did I draw the arrow there and then not start there? It's just not my day, I think. Okay, so we're going to make this y equals 4x minus 2 and 3 minus 5x. And then correct inverse notation is going to be g inverse of x equal to 4x minus 2 over 3 minus 5x. Okay, so there it is, squeezed in there, the end of my paper. Alright? Alright, so we're getting there. I just want to make sure you're prepared to handle all the different varieties you're going to see. Something a little different in this next one. This is a transformation of our parent function. So on this one we have that extra piece, right? what we want is a proportion. I want one fraction equal to one fraction so that I can cross multiply. But if I just make this side a fraction, well, now I have a fraction equal to a fraction, and then that minus 7, it's messing up my proportion. Okay, it's not a proportion with that third term in there. So we're actually going to start this one by adding the 7 over. Let me add the 7 over so that this becomes y plus 7 equal to 2 over x plus 6. And now I can make it a proportion. Let me stick my 1 under the y plus 7, and that 7 is no longer an issue. Okay? So now we cross multiply. 2 times 1 is going to be 2. And then it's going to get a little ugly here. We have to distribute a y plus 7 to an x plus 6. Okay? So 2 is going to equal, we have x times y, xy. We have 6 times y, 6y, 7 times x, 7x, and then 7 times 6, which is 42. Okay? So I need the terms with x's on one side and the terms without on the other. So I already have both terms with x's on this side. I'm just going to go ahead and leave them there. So in this one, I'm going to subtract over the 6y and the 42. So that's going to cancel them from this side. And again, subtract over the 6y and subtract over the 42. So what do we have all together here? Well, I'm still going to have a negative 6y on this side. I can combine the 2 and the negative 42 to make a negative 40. And on this side, I still have the xy and the 7x. And now I can factor out the x that those two terms have in common. So if I factor that out, I still have negative 6y minus 40 on this side. Factoring out the x leaves me y plus 7 on this side. And now I'm going to divide over that y plus 7. So divide both sides by y plus 7. And boom, x is all by itself. Okay? So here, x was all by itself equal to negative 6y minus 40 over y plus 7. Now I'm going to switch the x and the y, so y equals negative 6x minus 40 over x plus 7, and then I'm going to call it the inverse. So negative 6x minus 40 over x plus 7. And again, you could probably do that in less steps than I'm showing, but I just want to make sure that my work is nice and clear here. Okay, so there it is. And we haven't checked one in a while, so let's do a little quick verify on this one. Let's pick something to plug in. I'm going to pick strategically a negative 4. If I put a negative 4 here, negative 4 plus 6 is 2. 2 divided by 2 would be 1, and 1 minus 7 would be a negative 6, which means over here, I should be able to plug in a negative 6 and get a negative 4. So if I put a negative 6 here, that's going to be, and a negative 6 here, that's going to be 36 minus 40, which is negative 4, and then we're going to divide that by the 1 on the bottom, and we do in fact get a negative 4. So just a little quick check, and it worked. But I want to get rid of it because it makes my paper look ugly. Alright, so there it is. Another one, if you want to give it a shot and you're feeling confident. If you're not feeling confident, it's okay. This process is really hard. Okay, there's a lot of work involved here. Don't feel too bad if you're a little overwhelmed at the moment. Alright, let's see. We're going to move this 2 over so that we can make a nice proportion. So we have y minus 2 equal to 1 over x minus 8. And again, I'm going to make this a proportion. So I'm going to put a 1 underneath, and now we can cross multiply. So 1 times 1 is 1, and on this side we're going to have to multiply y minus 2 by x minus 8. So we have 1 equal to xy minus 8y minus 2x, and then plus 16. Just like the last one, I want to move over the terms that don't have x's. So I'm going to add the 8y and subtract the 16. Subtract the 16 and add the 8y. Cancels them from this side. So I have 8y, and then when I combine these, I have negative 15 left. And on the other side, I can factor out the x from the xy and the negative 2x. So 8y minus 15 is going to equal x times y minus 2. And now I can divide. Let me divide over the y minus 2. Divide over the y minus 2. And now we're good. X is all by itself. So we have x equal to 8y minus 15 over y minus 2. Now I'm going to switch x and y. So y equals 8x minus 15 over x minus 2. And then I'm going to call it the inverse. 8x minus 15, x minus 2. And there you have it. Okay? So this is, again, definitely a lot more challenging than finding the inverse of, let's say, a linear function. But this is good, solid college algebra that you should be able to handle. Just take your time. Try to follow the steps that I've outlined there if you get stuck, or at least follow an example that I've done if you get stuck. Okay. Now we've done some quick checks along the way to verify that we properly found the inverse. We picked an x, plugged it in, and produced a y, and then made sure the opposite effect happened. But as I mentioned earlier, and as we saw in our functions module, if we actually wanted to verify that two functions were inverses, we had to find their compositions. So remember, if I plugged a function into another and vice versa, and both times all of the operations canceled out, then we could verify the functions were inverses. Let me just show you with a linear example, okay? So let's say our original function was x plus 3. Then the inverse would be x minus 3, right? So if I took this function and plugged it, the inverse function, and plugged it into the original, well, that would give me an x minus 3 plugged in plus 3. And what happens with the plus 3 and the minus 3 is they cancel, leaving you x. And if I did this in reverse, if I took the original function and plugged it into the inverse, then I'd have an x plus 3 plugged in, and then a minus 3. But again, what happens to those? They cancel, and they leave you an x. And that's what's supposed to happen. If the compositions of two functions results in x both times, those two functions have to be inverses. So if f of g of x is equal to x, that's if g of x gets plugged into f and everything cancels and leaves you an x. Or if g of f of x equals x, that's if f of x goes into g and everything cancels and leaves you x, then f of x and g of x must be inverses. Okay, so to verify that two functions are inverses, we show that their compositions are both equal to x. Okay, so let's try this out. We have a function, here's our function, right? And according to number 4 here, this is its inverse. So if we want to verify that, we are going to plug one function into the other and vice versa. So let's start with y of y inverse of x. Okay, that is taking the inverse function and plugging it into the original function. So we're going to take this inverse and we're going to plug it into the original. But the original's got two x's, which means it's going to have to go here and it's going to have to go here. And this is going to look really ugly, but it's going to give us a chance to practice a bunch of our skills. Okay? So on the top of the fraction, I'm going to have 3 times, in place of x, I'm putting in the inverse function. So x over x minus 3. And then on the bottom, instead of an x minus 1, I'm going to have the inverse function minus 1. So it's going to be x over x minus 3, and then a minus 1. Okay, so now I just got to simplify it. Like, no problem. I just got to simplify this and make sure that everything's going to cancel. So how do I simplify this? Well, this is a complex fraction. Remember, if we can get all of the denominators to be the same, then they don't matter any longer. So this, technically this 3 can go to the top of this fraction. So our only denominator is x minus 3. So I'm going to multiply this 1 over here by an x minus 3 over x minus 3 to get it to have that common denominator. Now all of those denominators match, so I don't need to worry about those denominators anymore. I need to focus on what do I have in my numerators. So in this numerator, I've got a 3x. In this numerator, I have an x. And then here, I've got a negative 1 times x, which is a negative x. and a negative 1 times a negative 3, which is a positive 3. So what's happening here? Well, 3x on the top, and these will cancel, so just 3 on the bottom. And what happens to the 3's? They also cancel and leave us an x. Okay? So that's what was supposed to happen. All the operations were supposed to cancel and leave us an x. So we verified it in one direction. Now we get to verify it the other direction. And when I say we, I mean me, obviously. You're watching me do this, right? Okay, but ultimately the goal would be for you to be able to do this as well. So now we're going to go the other direction. We're going to find y inverse of y of x. Okay, so now we're going to take the original function and plug it into the inverse. So this original function is going to go here, and it's going to go here. Okay, so what's that going to look like? So instead of x at the top of the fraction, we're going to have the whole original function. So it's 3x over x minus 1 over, instead of x minus 3, it's going to be the whole function minus 3. So 3x over x minus 1 minus 3. And same thing now, we have this complex fraction. So let me make this a fraction. Get a common denominator, which is just x minus 1, so that I can get rid of all those denominators, right? Not worry about our denominators anymore. So we have room to work this way. Yep, gonna go this way. So we have on the first numerator, the top numerator, 3x. Right? Remember, once all our denominators are the same, we don't need them. And then in this numerator, 3x. And then in this numerator, negative 3x. And then negative 3 times negative 1 makes a positive 3. So that's going to be 3x over, these two terms cancel. And now the 3's cancel and leave us an x. Perfect. It's exactly what was supposed to happen. Okay? Since when we plug the function into the inverse and vice versa, since both times we got x, these are inverses. Okay? Verified. And yeah, so I know this is probably the toughest, maybe one of the toughest algebraic lessons we've seen thus far. You just got to be really careful with your work. I will tell you, the verifying of inverses piece here, something you should be able to do, definitely. I think on the quiz for this module, I'm not going to require that you do one of those. It may occur as a bonus question on that quiz, where you'd have to do the work on paper, take a picture, and then upload the picture. But I don't think that's something I'm going to require, just because, well, it's tough, all right? And it's honestly, it's not something you're going to be asked to do a bunch. It's really just good practice of our algebra skills, because it's practicing compositions and it's practicing simplifying complex fractions. But ultimately, the bigger goal from this lesson is that you can find an inverse function, and that's definitely tough enough. Okay, so do your best. Again, you've got practice problems to work on, so give those a shot, and then if you need some help, then just reach out.